The future holds many challenges for robotics in terms of AI and navigation, sensing and interpreting the environment, fine motion control, as well as capturing and manipulating objects. Such tasks are easy for people, but with the coming age of robotics, it is more important than ever for students to understand how to tackle these challenges. Our team was tasked with developing a soccer-playing robot, utilizing the aforementioned fields of robotics in accordance with the International F180 small size league rules. The robot needed to adhere to dimension constraints, be able to legally control the ball, and all processing had to be done on board. No external communication was allowed during play. Ideally, the robot needed to move at 0.5 meters per second, with the ability to dribble and then kick the ball at 2.5 meters per second. The ball, obstacles, goals, and walls should be easily detected, while the AI consistently acquires the ball, avoids obstacles, and kicks goals. Our final product is outlined throughout the video.
In relation to the software of the robot, a finite state machine was used to store the logic of the robot, and reactive navigation was used to find the movement logic for each state. A finite state machine was used so the robot could act independently and not rely on human input to make decisions. In total, there were 5 states: locate ball, seek ball, dribble ball, kick ball, and reposition. At first, the state of the robot is set to locate ball. Each state has several different entry and exit conditions. By the end of the semester, the software is at a point where the robot was independent of human interaction but was still quite basic. In relation to navigation, it was unfortunately overall very simple. All the navigation system did was get the robot to either rotate left or right until the object was out of screen. Extremely simple, and in the end, the robot was only barely capable of avoiding a single object. Overall, software was lacking, but the base for it would have allowed, if time permitted, to create a fine piece of code that was able to complete the tasks that were set by the EGB320 teaching team.
The vision system on board our soccer robot is based around the Raspberry Pi camera. The Pi camera was the obvious choice after some brief research findings. This mentioning the Pi camera is specifically optimized for the Raspberry Pi, along with its ability to have the auto white balance and exposure set to ensure consistent lighting in the camera feed. The complex frames imported from the Pi camera are then sent through color spectrum thresholding processes, breaking down the frames to reveal locations of relevant objects. These objects are then returned to the AI system as simple range and bearing values, allowing the robot to effectively see what's in its environment.
Our omnidirectional drive system provides the capability to move in any direction whilst rotating simultaneously. The software controllers required, however, and the AI techniques that would utilize this were not fully implemented on the demonstration day. Hence, simple movements are shown here instead. Continuous rotation servos and custom wheels provided minimal friction and plenty of torque, with possible speeds exceeding the requirements. 2 optical mice sensors were used as encoders, giving accurate velocity and displacement readings, regardless of any wheel or gear slippage.
The soccer robot was fitted with a kicker and dribbler. This allowed for the robot to retrieve the ball, control it, and kick it. A powerful kicker was implemented that can kick up to 4.7 meters per second. This allowed the robot to score a goal from anywhere inside the arena. The kicker uses a rack and pinion to compress a spring and release the energy into the ball. An end-stop switch was placed on the end of the kicker that allows the robot to pre-compress the spring and kick the ball quickly when preloaded. Reload time usually takes about 16 seconds between kicks. The dribbler uses a rotating cylinder that applies backspin on the ball, forcing the ball towards the robot. A deep V groove in the cylinder also helps the ball stay above the kicker while the robot moves.
Our final design did meet the minimum requirements for the soccer robot challenge, and the hardware has the capacity to exceed these. We personally feel, with the framework in place, that a little more development time would allow for the implementation of an exceptional system, with which the robot would surpass all expectations. Thank you.